All right, good morning, good morning. Welcome back. Happy Monday. I hope we had a great weekend. So we start on page 44 today. And while we're opening to 44, we'll take our quick look at the calendar. So today we continue talking about what is the integral for, and the applications we see today are going to have to do with economics. Next class, we're going to talk about distribution functions and probability. Also next class, we have a quiz. Today's class, the material is fairly short, and next time we have a quiz, so I think we're going to try to get through like today's material and then just go ahead and start the probability stuff to give us a jump on Wednesday, since we're going to spend some time taking the quiz first thing on Wednesday. So as usual with the quizzes, you can come 10 minutes early, so we can start at 8:30 on Wednesday if you're interested. And right now, Project 6 is up in the air for you guys. I expect that it's going to take some time to get through Project 6, so hopefully you'll have some time to start looking at it if you haven't yet done so. That project is due on Friday this week. Any questions on the calendar? Okay, and then one other thing coming up, you can see test number 2 is happening 1 week from today. You have the same resources that you have normally. There's a bunch of practice problems in the packet. I have sent out a PDF of the solutions, like the color solutions to those problems, and there are videos up on YouTube for those as well. This Friday is our review day for Monday's test. Okay. So that is that. Just a reminder, I announced this last time, but if you have any interest in learning about what it means to take an online class, there is a workshop happening today, noon until 1 in Core 307. Pizza will be served, so check it out if you have any interest in learning some more about what it means to take an online class. It's C307 noon today. Okay, so today we start on 44. We'll jump here to number 1. I had mentioned this class is short and next class is long. We'll dive into Big Tree McGee. Josiah.
Big Tree McGee is negotiating his first contract with the mutual bank. They agreed they're still having about the amount of big bonus per year. Smaller bonus.
Okay, so let's take a look at the different options here. So option number 1, we get the big signing bonus right now, $2 million per year every year after that. So I'm just going to make another column here just to give me a rough sense of the total. So how many millions is the first one worth? Yeah, with the signing bonus. Yeah, year 1. Or no, the option 1 all the way through. That's $12 million in total. And option 2 has a small signing bonus, 1 million, but then the salary increases every year. What's the total value of that one? 13. How come we can't just look at that and say 12 is bigger than 13? Pick option 2. Yeah, we're gonna invest the money, and we don't know what it's going to be worth down the road. In the bottom option, yes, you get 13 million, but when do you get most of it? Like right at the end. Whereas the first option, you get half of your entire total right on the first day of when you sign that contract. And so that money would have 3 years to grow throughout the period here. So we got to try to take that into account. Let's go down to part A for Ernie. Okay, so we're going to assume that Big Tree can take his money right away and throw it into an investment that will get him 10% per year compounded continuously. Any of you remember the formula that tells you how much money you have when you compound continuously? PERT, that's the one. So it used to be that, well, at least in previous classes with me, we called it A equals A for amount of money, but it was really the future amount of money. And so how about we call it FV for future value? That's what we're interested in finding right now. Okay, so what I'd like you guys to do in your groups is calculate the future value. There are a lot of calculations, like every one of these boxes is going to have to get hit with this PERT formula. And just to be clear, the signing bonus is given at the beginning of the first year. And the payments are given at the end of each of the 3 years. Okay? So we're going to sign today. We're going to get $6 million today. At the end of the first year, we're going to get our first $2 million. At the end of our third year, it's another $2 million. So I want to know the future value 3 years from now, at the end of the third year. So the $6 million, how much time is it sitting there? 0, right? You get that on the last day of the third year, and that's when our experiment ends. So can you guys, with your neighbors, do calculations? Once everybody knows what's going on, split up the work. It's the same calculation over and over again. All right, so I think all our groups got to 14.75 and 14.21. Any questions on using that PERT formula? Okay, and we don't yet have an answer on the updated question, which was what can we change that 1 to try to make the bottom row worth the same as the top, but 1.4. So I'll just put that there as like the bonus answer. If it's something you want to think about, change the 1 to 1.4, and all of a sudden they're equal. Okay, good. Let's move on to the next page. This is a different question that I didn't even ask every table. But the question was, what can you change the 1 to try to make the bottom row worth the same as the top? And so I think that right here, instead of that 1, you could put a variable. And then you'll have an equation equal to 1475, because that's the problem, is to make it equal what the top is worth. And then you could solve. Okay, on the next page, talks about calculating the present value of each contract offer. Present value. So here's what we're trying to do. Another way to think about the total value of these two things. So we have two numbers, 1475 and 1421. That's what they're worth 3 years from now when all is said and done, including the interest that you'd get on your investments. But another way to answer this question, or to think about comparing these things, would be to think about how much money could you be given today, so that 3 years from now you'll have exactly the same value as what option 1 was, or exactly the same value as option 2. So in order to find the present value, here's what we'll do. So I'm going to write down my my equation from before. Future value is PE to the RT. But again, I'm going to change the Your book uses a letter B for something. Yeah. So I'm going to cross this off and call it a B, because that's what the book uses. I don't know what it's supposed to stand for. But if B is the future value, can you look up there and decide, I mean, like, what letter are we using for how much you invest today? Is P. And so we're going to call P the present value, how much you put in today, and then it grows to some future value. So if we're looking for the present value of something, it's just a matter of solving this equation for P. So let's divide both sides by e to the RT. And then I'll just write that as BE to the negative RT. And just like I used FV for future value, I'm going to call it PV for present value. So that's how we find the present value. So let's see if we can use, so I'm going to circle this. This is now just as important as the PERT formula. PERT formula tells you what you have in the future. This formula right here tells you what it's worth today, what some future dollar amount is worth today. So let's do one of these calculations for one part of this example. So let's go ahead and I'm going to grab this number right here. We'll just do one calculation with this. So $4 million given to you at the end of 2 years from now, and then letting it grow for one more year, because that's how long that $4 million grew for, I want to know, well, okay, what is that really worth if somebody were to just hand it to me today? If you were to hand me a check today, and we wanted it to be worth $4 million 2 years from now, are you handing me a check for more or less than $4 million? I'll say it again. If you hand me a check today, and I want to be able to throw that money in a bank and have it become 4 million exactly 2 years from now, are you handing me something for more or less than 4 million? Less than 4 million. So we just want to know what it's worth today. What can you hand me today so it becomes 4 million? So let's do that for the present value calculation. So for example, the 4 million is the only 4 in the table. So we use our formula here. It says PV is equal to BE to the minus RT. B is what we're calling the future value for some reason. What are we hoping the money grows to? 4 million. E to the minus. The interest rate is still 10%, so it's still 0.1 here. Times T. How much is T? It's 2 years. That's how long the money grows for until it's supposed to magically become 4 million bucks. So we type this in the calculator, we'll get some number a little less than 4 million. How much? 3.27. So that is the present value of 4 million 2 years from now. Make sense? Just another way to think about future value, just looking at it from today's perspective. Any questions on what the 3.27 represents? Okay, then what you could do to answer the previous question, you've already decided which option is better. We all agree option 1 is better, but let's pretend we haven't done any of these calculations here at the bottom. In order to figure out which option is better, instead of doing a bunch of future values and adding them up, we could do a bunch of present values and add them up. We just found 3.27. That's the present value of this particular $4 million check. You could do the same thing. You can calculate the present value of the $6 million and the $2 million and the 1 million signing bonus. You'll get some number, which is the equivalent of somebody handing you that one check today and saying, I'm not paying you again another dime for 3 years. But you better believe that 3 years from now, it would grow to exactly 14.21 million if you just threw it all into the bank today. So just another way, it's like, you know, the other side of the same coin. All right, let's move on to number 2. We see some formulas from pre-calculus. So we've already seen the PERT formula. Now we see the BE to the negative RT. It's just solving for the other letter. Most of the examples we'll do will involve continuous compounding, but you might remember from the pre-calculus class there were annual compounding formulas, P times 1 plus R to the T. And then you can again solve that one for P, and that gives you this formula. So let's move on to Richard for 3. Okay, so I've added an example here, so maybe you can squeeze that in on your paper. P of T equals 400 times T plus 1 squared, and the units there are dollars per year. So let's just plug in a few numbers to try to get a sense of what that formula represents. If we plug 0 in, what do we get? 400. So imagine that you own some company, and in your at the start of your company, you open the doors at time 0. Your company is making $400 per year. If you're more ambitious, make it thousands or millions or something like that. But we'll just call it $400 per year, okay? But your company is going to grow. So 1 year into this experiment, into your company, what do we get when we plug in 1? 1,600, is that right? Super. So 1 year after opening the doors, your company is now making $1,600 per year. Things are going so well. We'll have an IPO. Let's see what happens after 10 years. So plug 10 in for T. And what do we get? Thank you. So at that moment in time, we are making $48,400 per year. Okay? Could we plug in a decimal? Could I plug in 0.5? You can. So we're not saying that the $400 comes into your door on that first day. Just at that moment in time, your company is making $400 per year. But if you wait half a year, you're going to get something more. It doesn't just jump from 400 to 1,600. It's a very smooth, continuous kind of transition. And so instead of thinking of the money coming in, like in discrete intervals, we can think of like little fractions of pennies just getting added to our bank account at every second of the day, right? And so this is how we translate from like a pre-calculus problem, like the basketball player, to a calculus problem right here. Because if I want to know, what is $400 worth, what is $1,600 worth, I can't just plug into a PERT formula, because if you wait 1 second, the 1,600 is now is increased just a tiny bit, right? Every second that you wait, you're making just a tiny bit more money than you were before. So that's where the calculus comes in. Units are dollars per year. All of those are dollars per year. Okay, so let's. So suppose that you were making this $400 per year, and I want to find out, what it's worth 1 year from now. If we were just using PERT, I handed you $400 today, we could throw it into the PERT formula, right? But we're not getting $400 today. If you divide that by 365, number of days in a year, it's roughly 1. Let's just call it $1 a day. So what would I do? Well, I get $1 today. That gets to grow for almost the entire year. Then I get another $1 tomorrow. That grows for a little bit less time, and then another $1 the next day. And you can see that there are a lot of calculations involved all of a sudden. But even saying you get $1 per day is a simplification. You really get, all right, 24 hours in a day, so something like 4 cents an hour, roughly. So really, we should be doing 4 cents in the first hour, and then figure out how much interest we get in a year, and then 4 cents the next hour. But really, that's an exaggeration again. And so you can see we're cutting it into tinier and tinier pieces and getting closer and closer to reality. The reality is you have like a stream of pennies, fractions of pennies happening all the time. So let's see how we handle it with calculus. We'll go to number 4, and we're back to David. Okay. Okay, so let's take a look at our picture. We're going to start the clock when we open our doors at time 0. M is the number of years that we're going to let this experiment run. And then you pick some generic moment of time to really focus on. So we're calling it time T, some number of years since we've opened our doors. And we know, we could figure out what P of T is at that moment in time because you've got a formula here in front of you. So maybe at that moment in time, you're bringing in $1,600 per year. The idea is you want to let time pass, but not too much, because if you let a bunch of time pass, then this 1,600 increases significantly. So we're just gonna call it a little tiny time interval here. We're going to trust that the 1,600 doesn't change too much, and then we're going to use some of our formulas. So let's look at this next part right here. It says the future value on the tiny time interval pictured is. Okay, future value. We've had 2 formulas today. Is this PERT or is this e to the negative RT? Future value is PERT. So we're just doing PERT. The principal is the amount of money that comes in at that one moment in time. I don't know what it is, but it's P of T, dollars per year. That's what we're calling P of T. Maybe it's $1,600 per year at that one moment in time, just at that second. Times e to the interest rate is what it is, and then how much, T represents how long the money is going to grow. So it's a little bit confusing because we've got a T here, but really we know that the number that goes in the PERT formula is how long the money is going to grow. How long is this money going to grow? It's this M minus T. See it? M is the total amount of time that you're going to invest. T is how long it's already been. It's the moment it's present. It's what we're focusing on. So it has M minus T years to grow. So that goes right up here. And hopefully that reminds us of our little example where I said we were making, what did I say, about $1 a day. So today's dollar at the very start has 365 days to grow, but tomorrow's dollar has only 364, and the next one has only 363. That's the M minus T. Right? You have a year, but then you got to subtract all the time that's already passed. Okay, super. So then we won't be so surprised when we end up with an integral. And so this guy right here ends up being in the integral for future value. You guys could be more excited about this than you are. I'm just saying. Yeah. Okay, so that formula looks pretty similar to the formula we just had. You throw an integral in front of it because really what you want to do is add up all your little, you have like 1 million different bank accounts, essentially. You're adding up the future value in every little one of your million bank accounts. So that's that, and then the present value we haven't seen, but it looks an awful lot like the BE to the minus RT, just inside of an integral. All right, and so now we're going to do an example where we use those formulas, or one of them anyway. Oh yeah, we'll use both, but it's really not that interesting to use the formulas. Using the formulas is cake easy, like it is in many of the integral examples. It's really about getting to that formula that I think is the interesting part. Okay, we'll go to Maggie for 5. Okay, and so we're going to update just the sentence that Maggie read from. I wanted to make it a little more complicated than just $20,000 straight. So if we can use that same function that we came up with before, 400 times t plus 1 squared. Yes, yeah, instead of 20,000, let's use that formula. Okay, so let's start with the future value. That's one we have a lot more experience with. I want to know, what are we going to have at the end of this 10-year process? Let's come back up just to get a sense. See those numbers there in purple is what we calculated for this income stream function. In our first year, or at least at the first moment in time, we're making $400 per year. Then 1 year into it, we're making $1,600 per year. In the 10th year, we're making $48,400 per year. So in some sense, you could do 10 of these numbers and add them all up, and that will give you a rough estimate. But what does adding these numbers up not take into account? The time in between and all the interest that we earn, right? That $1,600 or the $400, part of that comes in on the first day. A few fractions of pennies comes in on the first day. We're going to invest that. It's going to grow for 10 years. So you could get an underestimate by doing 10 of these numbers and adding them all up. But let's just jump to the final answer. So future value, according to this formula, is an integral. 0 to m. M is how long we're waiting, how long we're investing. 10 years. So we go 0 to 10. And then it goes P of t. What is P of t in this example? It's that 400 thing. And the next part of the formula is e to the r. What's the interest rate? 104. And then in the parentheses, we put m minus t. What is m? Still a 10. What is t? T is t. T is the variable. This is an integral with a dt at the end. That t right there belongs. Don't replace it with anything. Any questions on the pieces? M is a time. Yeah. I feel like banks use M for mortgages. Like if you have a 30-year mortgage, then M is 360 months. So I wonder if that's the motivation for the reason we use M in this book. Okay, so let's type that integral in. Technically, I think we could do it. It would require some work to do this by hand, but I do believe we have the techniques to do it. But really, I'm just interested in the bottom number. So let's, the bottom line, I should say. So let's get a number here. This is going to tell us, what's that? Yeah, exactly. So this will tell us how much our company will be worth over this 10-year period. And we've got a few folks doing that. And the rest of us can start the other calculation, present value. It's the formula in yellow. Go ahead and write down the formula to calculate the present value of this company, again, in 10 years. Anybody get something the same or different? Tiffany, same? Okay. Anybody got something else? Okay. Uh, 0.04. 32 is at the end of this, Ernie? Right, okay. All right, and then the present value formula, a little bit different. In this case, still 0 to m, so 0 to 10. And P of t is still the blue 400 formula. Let's move this up a little bit. Great, thank you. So I feel like just under 200,000, that's the answer we're getting. Okay, so the next thing that goes here is this P of t, which is the 400 times t plus 1 squared. And then it's e to the minus rt. So e to the minus what? 0.04, and then t is t. And that right there will tell you the present value of your company today. What is it? 192. Okay, see if anybody else can confirm or got a different number. And there actually is a really easy way to check that these two numbers kind of agree with each other. Not to say they're right, but you know how like sometimes piano tuner will just tune the piano to itself? Just pick one note and call that one the right, and then tune everything else. So here's an easy way to at least see that these two dollar amounts are in tune with each other. The whole idea with the money is that your company's worth 133,000 today. Meaning if you take that 133,000, put it in a bank at 4% interest for 10 years, it should grow to the future value of your company, which is 198,000. So if you type this into your calculator, so we're go back to the pre-calculus way, A is equal to PE to the RT. If you just put in that 133 as your P, E to the 0.04, now how much is T? It's 10 years for the whole life of this experiment for your company. We should get something very, very close to the 198,639. How close is it? E to the, where's my E button? 0.04 times 10. Something is very bad. Second, I like the second number better though. Let's see, times is that button. 198, 639, 32, yeah. So, once you know one number, it's very easy to get the other one, but it's nice that the integrals are in tune with each other. So I don't have the numbers, but recently in the news, there was some like mega jackpot that somebody won. Yes, anybody follow this? I heard that this wasn't on the news, but I heard some people around me reacting to the news angrily, talking about how the person who won wasn't even a citizen and our government should step in and, like, but whatever it is, if you win one of these like Mega Millions jackpots, there are two options presented to you. There's the option that you see in big bold letters on the huge billboards on the highway. That's the one that's on the radio ads as well. It's now at $230 million. Or there's the other option, which they don't promote. But the two options are not, well, they're supposed to be worth the same, but you don't get a check for $230 million if you win this thing. That $230 million is spread out over like 20 years. And so if you add up all of the checks you get, yes, it is 230 million, but it's over 20 years. So you don't have the interest for 20 years, and that's pretty significant. So I think that what we might be able to do if we had these numbers, and I don't have them in front of me right now, but if we had them, we might be able to estimate. So I think the theory is that if you just get the one check today, it's going to be a lot less than 230. But the idea is it should grow into something that's worth the same as your 20 different checks. And so in order to figure out how much they should cut you a check for today, they're assuming some interest rate. And I bet we could use the ideas that we've got here to figure out what interest rate the lottery companies are assuming. Yeah, Angus. Right, right. And I bet the companies know exactly these formulas and make sure they're making a profit when all is said and done. Okay, so on Project 6, there are 3 questions. Project 6 is the one where the first question is about work and raising, I think it's water, but it might be gasoline, I forget, out of a tank that's buried in the ground. What is it? Gasoline. So we're taking gasoline out of a tank that's in the ground. A second problem, and I don't have the order in front of me, but another problem involves finding the mass of a whole bunch of the atmosphere. And a third problem involves an economics thing. And so what you're going to have an opportunity to do is really think carefully about what the income stream idea is and what does it mean to actually calculate how much the money that's happening in this tiny little interval grows to, and then adding up all the pieces and eventually getting to an integral. So the problem on the project could be tackled in one fell swoop by just writing some stuff inside of an integral, but the project is supposed to kind of lead you very carefully through why the integral is the right tool for that one. You will use the integral at the end of the question, but it's a bunch of parts, and the parts kind of lead to the integral, as opposed to just starting with some pre-cooked formula like that one. All right, so then technically now you have all the tools you need to answer all 3 of those questions on the project. So again, hopefully you'll have some time soon to give it a look. Okay, so I had mentioned that there are resources for you on the test. They begin on the very next page, page 46. So there's a study guide there, list of topics I'd like you to be very familiar with. There's on the next page, there are some problems that were never assigned for homework that you can check out. And then on the next page are the sample test problems. And again, the YouTube links should be working as of this moment. The test is 1 week from today. Yeah, so we have one more day of new material, which we're actually going to start right now. So we're starting on page 51. So the last thing that's going to be on the test has to do with probability, which is here. So we'll start it today. We'll get a good jump on it. First thing Wednesday, we'll take our last quiz before the test. Then we'll finish this probability stuff. Friday is our full period review, and then Monday is the test. All right, so let's take a look at number 51, which involves an age distribution example. I just copied this chart from your book. So let's analyze the chart and see what's happening here. So this chart gives the distribution of ages in the US in 1995. So if you look at the age group 0 to 20, 29% of the entire US population fit inside of that age group. 20 to 40, that was 31%, 40 to 60 is 24%, 60 to 80 is 13%, 80 to 100 is 3%. So surprises, not surprised? Did we expect the numbers to peter off like that? Yeah, because people die. So you're not going to find a whole lot of octogenarians and centenarians. I think that's the right word. The numbers maybe make sense. We've got the same information listed over here as a histogram. So 0 to 20 represents 29%. Same thing that's over there. And then it goes on until we can see the peak and then kind of trailing off as people get older. And I just want to be clear about what these numbers are, because 0.01 and 0.015 is not anywhere in this list. So what the axis over here represents is the fraction of population per year of age. So let's assume for the time being that these 0 to 20-year-olds, that 29% is evenly distributed in between the zeros and the 20s. So there's exactly the same number of people that are 20 as 19 as 18 as 17. They're all equal numbers of each age. It's not true, but let's just assume it for a second. How could I figure out if 29% represents everybody, how much is each single age year? What would I do to 29%? Divide by 20. So let's take 29%, divide it by 20. And what do we get? 1.0145. That is to say, if we assume that there's the same number of people who are 20 years old as 19 as 18, then each single year represents 1.45% of the overall population. So 1.45% of the US population is 20 years old, 1.45% is 19 years old, 18, etc. So that 1.45 is the height of that rectangle. You understand that number, what the vertical axis represents? Okay, so let's see if we can answer some questions using the data up here. So first one says, estimate what fraction of the 1995 US population was between 20 and 60. Okay, between 20 and 60, we have two numbers. What do we do with them? Add them. So we got 31% plus 24%. Assuming that the chart is perfectly accurate, is this 55% an estimate or is it the exact answer? It's exact. If we believe the chart, then we believe exactly 55% of the population is between 20 and 60. Well, let's come to one that's going to be tougher for us. I want to know what percentage of the US population is between 75 and 80 years old. This is tougher because I don't have a 75 to 80 block. It's not a nice block of 20. So 75 to 80, let's see. So 70 is right here in the middle. So 75 is again in the middle there. How about we assume that the 60 to 80 year group is again perfectly distributed. So there's exactly the same number of 60-year-olds as 61-year-olds as 62-year-olds. So could we figure out what part of that block is between 75 and 80? Yeah, so we can do a quarter of it. That's kind of the quick way. We can do a quarter of the 13%. So what do we get here? Is that 3 1/4? 0.25%. We could do a little bit more work and figure out if that 13% is cut into 20 equal pieces. And then how many of those pieces are we interested in? We want 5 of them. So you'd get the same answer by dividing by 20, just like we did with the 29, and then times 5. So our best guess at this point is that 3.25% of the US population is between 75 and 80. Assuming we believe everything in the chart and only what's in the chart, is this an exact answer or is that an estimate? Is it? What did we have to assume in order to do this? That it was uniform. We had to assume the same number of 80-year-olds as 61-year-olds. The graph being drawn flat assumes that it's evenly distributed, but we know better, right? I mean, even if this 13% is the perfect number, with no more information, that is an estimate at best. And in fact, we can, yeah, I mean, the flat is all you can do. You've used every data point and you just connect the dots with flat lines. But we can figure out if the 3.25%, do we believe it's an underestimate of the real answer or an overestimate? Can you chat with your neighbors? 3.25% is our estimate. Do you believe that that it is under or over the true number, which is the percentage of people that are between 75 and 80? Thoughts? Is 3.25 over or under the true number? I heard over, I heard under. Other thoughts? Yeah, in order for it to be the right answer, we were assuming that the number of 61-year-olds is the same as the number of 79-year-olds. But in practice, we expect there are going to be more 61-year-olds than 79-year-olds because there will be people in between who didn't quite make it. So 3.25% feels like it's going to be an overestimate. It's the best we can do with the data we have, but it feels like it's an overestimate. And then if we go to the next question, it says between 80 and 85. So 80 to 85 is our last rectangle. 90 is there. 85 is not there. 85 is here. So what do we do with the 3% to find that piece? Again, we'll take 1/4 of it. So 3% and then 1/4 of that. So about 0.75%, a little less than 1% of our population is between 80 and 85 years old. What's that? These were the real numbers from 1995, yeah. So do we think that 0.75 is under or over the real number? That's going to be under, because most of the people that are between 80 and 100 years old today are closer to 80 than 100, right? And so that one should be an underestimate. Okay, fair enough. Let's look at the next page. And we're going to see the same information, but now we have a little bit more data. Instead of going between 0 and 20, and then 20 and 40, we have them broken up into groups of 10. So we have some more information. And so all those rectangles get a little bit thinner. And if we kept up this process of making the rectangles thinner and thinner and thinner with more and more data, eventually you get something that would look kind of like the blue curve that we see up here in this picture. And so that blue curve represents the age distribution of citizens here in the US. Where do you see it dip back up? Okay. Why? It's interesting. That is interesting. You know, I mean, that's the question is like how much control, if any, do we have over like how long we live? I mean, Certainly, like the food and the exercise and all that stuff is important, but I think Cole is just talking a mental exercise right now, like your will. And I mean, like I've this is just anecdotal, but like I've heard lots of times when like an old married couple, like will die within a few months of each other, like as soon as one person dies and the other one doesn't. And so I just, there might be some merit to that, just the mental part of it. Okay, and so if we take a look at the idea that we had before, which was to essentially we were finding areas of little parts of rectangles, right? I kept shading in parts of rectangles. So if I wanted to find, for example, the probability that, or what percentage of the population is between 80 and 90, then we would just look at the rectangle between 80 and 90, yeah? And then we'd find its area, whatever it is, that's what we've been doing. In this case, the area is just 2%, that's what it says, 80 to 90. Okay, but that's an approximation, right? Because we're assuming that the people are evenly distributed between 80 and 90. Okay, so suppose that they aren't. Suppose that the real distribution is given by this part of the blue curve. That's reality. Well, how much off are we going to be? Well, what should we really be finding for that red curve right there if I want the percentage of people that are between 80 and 90? I really want an area. I want the area underneath the red curve, yeah? That's going to give me the percentage of people that live between 80 and 90. It's just like the rectangle, but that's the right answer, is the area under the curve. Tells you what percentage of people are in there. But if you approximate the area under the curve with the rectangle, well, you'll be off by some, but the rectangle is blown up here. This is your, oh, did I pick the wrong rectangle? I guess I did. I thought we were doing between 80 and 90, but actually this rectangle is between 70 and 80. So if we look at that part of the curve, and we're interested in the area inside of there, that would be the right answer. But if we just grab the area of the rectangle, which is the easy answer, how much error have we made? Well, if you look at the blown up version of this picture, you can see that there's some stuff that I should have gotten. These are some people that I wanted to count but didn't. And here are some people that I should not have counted, but I did because they were in the rectangle. But they almost cancel in this picture, right? It's not going to be too far off the estimate that we get from using the rectangle. Okay, so let's go on to number 5, and I think we're up to Dawn. Okay, let's pause right there. So the idea with this new concept, this probability density function, is that it wants to be something like this, where if you want to know what fraction of the population lives between, and then we'll make up numbers that aren't in the chart. Let's say that this here is 27, and over here this is 32. If I want to know what percentage of the US population is between 27 and 32, really what I want is the area under that curve. That's what I want, because the curve is basically just a bunch of rectangles, but if you have fine enough rectangles, then it becomes just a nice little curve up there. So that histogram, that curve, represents a probability density function because the fraction of the population between A and B, between 27 and 32 years old, is exactly the area under the curve between A and B, which you can write as an integral. All right? That's the key feature for this new thing called a probability density function. There are 2 other little notes in order for it to be a probability density function, but essentially the first one is the main one. That's what we're after. So let's look at the last one. Lots of symbols here. It says the probability is bigger than or equal to 0. This upside down A, anybody seen that math symbol before? That means for all, thank you. So this says that P of X, the curve, is bigger than or equal to 0 for all X. Is that true for the curve that we have up above? Is there any age that you can plug in for X where you'd expect a negative answer? No way, right? It wouldn't make sense, and it doesn't make sense for PDFs. So always bigger than or equal to 0, Cassidy? Yes, it's really an upside down A for all. And if we're being very fancy, you can also throw a backwards E in there. Yeah, so this there exists, and then usually it's a 1. There exists some. Yeah, so it's not every, but just one. Okay, the other thing, if you find the integral of the curve, that blue curve up there is what we're now calling P of x, from minus infinity to infinity. Well, let's think about this. You're really finding the area underneath the entire curve. What would we get for the area underneath this whole curve right here? It better equal 100%, right? Because every single living person is there somewhere. And so we are going to get 100% of the population. And in fact, assuming there's no error with these numbers, if you add up all these percentages, you will get 100%. So the area underneath the whole thing is supposed to be 100%. We're just going to write that as a 1. All right, so take a look at number 6. Number 6 represents a very simple PDF. Hopefully this isn't the same US population age example. Can we think of something that we could measure where a lot of people have some characteristic that's a 0, but then it decreases until we get to a 4, and then nobody has this characteristic, right? It's 0 from that point forward. I haven't really thought about it. Anybody have any? What is it? Height in meters? How's that? Is that good? There are a lot of people who are, well, part of it works.
Yeah, I guess.
So you could say there are a lot of people that are 0 meters tall, not as many who are 1, not as many who are 2, and then once you get past 4, nobody at all, right? Fair enough. What's that? Number of semesters of calculus taken. Number of times imprisoned. Most people not imprisoned at all. Some people imprisoned 1 time, 2 times, 3 times, and then nobody in there after 4. How many times you've taken calculus? Well, it's a 4-semester sequence, so we can't get past 4, right? Most people take no semesters of calculus. What's that? Number of lost limbs. Nice. So I knew you guys could come up with some. Yeah. Okay, so then what we need to do is find the value of C because we can, so right now we're just basically saying most people have 0 lost limbs, and then some have 1 and some have 2 and some have 3 and down to 4. But really there is one magical number that we got to figure out for C because we got to make sure every person is counted somewhere, right? According to how many limbs they have lost. So what must be true about this space? What equals 1 about that space? Its area. So that's what we're after, right? Find the number C to make the area equal to 1. Okay, so area of a triangle, we know half base times height. We are going to make the area of this triangle 1. Half of, what's the base? 4. What's the height? C. Now we find C. Did you do an integral? No. How much is C? Is that right? C is 1/2. What does that 1/2 represent in Angus's example with the limbs? Fully limbed? You said number, the fraction of the population, right? Right, so 50% of the population has lost 0 limbs, and then it goes down from there. This is an atypical cross section right here. Yeah. Yeah, that's right. Okay, good. Next page. Okay, 7. We are back to Bubba. Okay, so here's the PDF. What is the least number of tons of fish that we might catch on a given day? 2. You can see 2 tons is the first point. What's the most we've ever caught? 8. What's the most common number of tons that we catch? Is 6, right? Because that's where the probability is the highest. The fraction is the highest. Okay, so let's answer the question here. It says, find the percentage of days where they caught between 7 and 8 tons of fish. So you have 7, you have 8. What are you trying to find for that, the picture? Is the area. That's the key part of the definition. If you have a PDF, then the probability of being between two numbers is exactly the area under that curve. So all we need to do is find the area between 7 and 8. So go ahead and calculate that area. Okay, so you calculate the area. I know the trapezoid area formula. If not, I know a lot of folks cut it up into a rectangle and a triangle on top. It's fine. So 15%. 15% of the time that we go out fishing, we catch between 7 and 8 tons of fish. Great. What if we go down to the next question here? I want the probability that this boat will catch between 7 and 8 tons of fish on a given day. What's the probability? It's 0.15. It's the same 15%. So the percentage of days that we go out and catch between 7 and 8 is the same as the probability that you will catch between 7 and 8. Okay, so just another way to think of the same thing. 15% there. Okay. So we haven't really done any calculus in terms of this yet. The calculus is coming in these examples here at the bottom of this page and then on the next page. Aside from the fact that finding area under curve is a calculus problem, it was easy to do the area here because it was just a trapezoid. But if I just gave you a formula for that curve over there, you would use calculus to find its area. So I see people packing up, but we have like 90 seconds left. That's oodles of time. So here's the idea we're going to start with next class. We've got this PDF, the probability density function, which I'm hoping we have a good sense. The most important thing here is that the area under the curve represents a probability, represents a percentage. But next time we're going to start with this thing called a cumulative distribution function. Cumulative distribution function. And it comes from some probability density function up above. Let's look at this picture right here and imagine we're going to start a new graph right here at 2. What's the probability that we catch less than 2 tons of fish on a given day? None. We never catch less than 2. So I'm going to start drawing a graph down here which says that none of the time do we catch less than 2. So that none of the time represents 0%. It's right there on the axis. But then we start to pick up and we start to catch some fish. So between 2 and 3, here to here, we do catch some fish some of the time that's between 2 and 3 tons. And so we're going to start to see this curve pick up as we capture days where we catch between 2 and 3 tons of fish. And it's going to pick up. I don't know exactly what it's going to look like. It's never going to decrease because this is a cumulative. And at some point, we're going to get up to 1 on this axis, and that will be the end of the game. And it's going to stay up there at 1. And it's supposed to represent the probability that you catch less than some number. What percentage of the time do we catch less than 8 tons? 100% of the time. So as soon as we get to 8, we've got 100% of the days, and it's just a matter of how are they distributed in between. Okay, we'll pick up there next time. The homework is not assigned on this section. Remember, we were jumping ahead. So the homework is just the economic stuff. We'll assign this on Wednesday.